Look at our planet from space, and what do you see? A swirl of white clouds, brown land, and blue. Deep, profound blue. That blue is Earth's lifeblood, its water, and it covers over 70% of our world. We see it in the inky, sapphire darkness of the open ocean and the electric, crystalline turquoise of a Caribbean bay. We see it in the milky, jade green of a glacial lake high in the mountains, a color so vibrant it almost seems fake. And yet, in a glass from your kitchen tap, that same water looks perfectly clear. How can one simple molecule, H2O, show up in such a dazzling spectrum of colors? What turns the clear water in your hand into the deep navy of the abyss, or the brilliant aquamarine of a tropical paradise? The answer takes us on a journey into the physics of light, the chemistry of water, and the geology of our planet. Wait. It's a story of energy, absorption, and reflection. For centuries, people figured the ocean is blue because it reflects the blue sky. It's an intuitive answer. Sunny day, blue sea. Cloudy day, gray sea.
It makes sense, right?
But it's also one of the most persistent scientific myths out there.
While the sky's reflection plays a small part, it's not the main reason.
The proof is simple. The ocean is still blue far beneath the surface, where you can't see the sky. The proof is simple. The ocean is still blue far beneath the surface, where you can't see the sky. The proof is simple. The ocean is still blue far beneath the surface, where you can't see the sky. The proof is simple. The ocean is still blue far beneath the surface, where you can't see the sky. The proof is simple. The ocean is still blue far beneath the surface, where you can't see the sky. The idea that the ocean is just a giant mirror for the sky is compelling, but it doesn't hold up. Reflection adds a bit of surface glare, like the shine on a wooden table.
The table has its own color, but you can still see the ceiling lights reflected on its surface.
If it were just reflecting the sky, the ocean would look silvery blue on clear days and turn a dull, flat gray under cloud cover, which it doesn't. The real story is a two-part process: absorption and scattering.
It all starts with sunlight.
What we see as white light is actually a cocktail of every color in the rainbow. You see this yourself anytime a prism or a rainbow splits white light back into its components: red, orange, yellow, green, blue, and violet. The key difference between these colors is their wavelength. Red light travels in long, stretched out waves, while blue and violet light travel in short, energetic ones. When this full spectrum of light hits the ocean, the water molecules act like bouncers at a club.
They are exceptionally good at absorbing the energy from longer wavelength light.
The long wavelength colors, reds, oranges, and yellows, get stopped at the door. Their energy is absorbed by the water and converted into a tiny amount of heat. This absorption happens fast, completely absorbed.
A little deeper, the oranges and yellows vanish.
By the time you're 100 feet down, even most of the green light has been filtered out. So, what's left? The short wavelength blues and violets. Water molecules aren't as good at absorbing these high-energy waves.
This is the first half of the secret. Water is a natural red light filter.
But this only explains why blue light survives.
Not why the ocean looks blue to us. For that, the blue light has to get sent back up to our eyes. That's where the second part comes in, scattering. While water is amazing at absorbing red light, it's pretty good at scattering blue light. Imagine a photon of blue light traveling through the water. It might strike a water molecule and get shot out again in a random new direction, left, right, down.
Or, crucially, back up toward the surface.
So in the open ocean, you have a two-step process. First, the water acts as a massive filter, absorbing the warm colors. Second, the remaining blue light gets bounced around by water molecules, and a good portion of it is redirected back upwards, out of the water, and into your eyes.
What you see is the light that the water rejected. You see blue because blue is the color that water spares and sends back out.
So why does a glass of water look clear?
It's a matter of scale.
The blue tint of water is incredibly faint. In a small amount of water, there aren't enough molecules to absorb a noticeable amount of red light.
Light passes through the glass, almost completely unfiltered.
It takes a huge volume of water, dozens or hundreds of feet, for this filtering and scattering effect to become strong enough for us to see that deep blue color. Now that we know water is a natural blue filter, we can tackle the deep, dark navy of the open ocean. When you're in the middle of the Pacific, far from land, the water below seems almost black. This is the purest expression of water's color, and it's dictated by one thing: extreme depth. Imagine being on a ship where the seafloor is thousands of feet down. Sunlight hits the surface, and its journey begins.
As we know, the water immediately starts absorbing the long wavelength reds and oranges. The light that continues down is overwhelmingly blue.
But even blue light can't go on forever.
In even the clearest ocean water, sunlight effectively disappears around 200 meters, or 650 feet. This area is called the photic zone.
Beyond that, the ocean descends into total darkness.
This means that in the deep ocean, there's no bright, sandy bottom for the light to bounce off of and return to the surface. The light just keeps going down until it's completely extinguished. The ocean essentially swallows it whole. The deep blue we see is the light that has been scattered back up to the surface from the upper layers of the water. We are only seeing the blue light that made a partial journey, got scattered, and managed to escape back to our eyes.
Any light that wasn't scattered near the top continues its one-way trip to the abyss.
This is why the deep ocean looks so dark.
The blue isn't bright and vibrant because there's no reflective surface at the bottom to amplify it. We're just seeing scattered blue light against a backdrop of pure blackness. The more water there is, the more light of all colors gets absorbed, and the darker the blue becomes. The water's clarity is also a huge factor. Open ocean water is incredibly puke, with very few particles. This means the color we see is almost entirely from sunlight interacting with water molecules themselves.
The fewer particles, the deeper and purer the blue.
When you look at the seemingly infinite navy of the open sea, you're seeing the true, unadulterated color of water itself. If deep ocean blue is a story of absorption and darkness, the brilliant, glowing turquoise of a tropical beach is a story of reflection. This is where the color and brightness of the seafloor change everything. Picture a shallow lagoon in the Bahamas.
The water is an electric, almost surreal shade of turquoise.
This color comes from a perfect combination of conditions. The water must be clear,
It must be shallow, and the bottom must be bright and reflective.
Let's follow the light again. Sunlight hits the surface of this shallow lagoon.
The water starts its filtering job, absorbing reds and yellows.
But because the water is shallow, maybe only 10 or 20 feet deep,
The light hits the bottom before it can all be absorbed.
in these tropical spots, the bottom is often brilliant white sand. This bright surface acts like a giant submerged mirror, reflecting the light straight back up.
Now, that light has to make a return trip through the same shallow layer of water.
The light has been filtered twice, once on the way down and once on the way back up.
The reds don't stand a chance.
However, because the water is shallow, it isn't deep enough to filter out all of the green and some yellow light.
What gets reflected off the sand is a mix of the surviving blues and greens.
As this mix travels back to the surface, it scatters.
And the color that emerges isn't the deep blue of the ocean, but a vibrant, shimmering blend of blue and green that we see.
The white sand is key. It reflects a huge amount of light, making the water seem to glow from within. If you were in a shallow bay with a dark, muddy bottom, the water wouldn't look turquoise. The dark bottom would absorb most of the light, and the water would appear dark and murky. So that breathtaking turquoise is a perfect team effort between light, water, and sand. The water provides the blue filter. The shallow depth lets some green light survive. And the white sand provides the bright canvas that sends that beautiful blue-green light back to our eyes. So the rule is, deep, clear water is blue, and shallow, clear water over a bright bottom is turquoise.
But nature loves to break the rules.
We've all seen water that's murky green, muddy brown, or even a startling, milky jade. These colors are caused by the final piece of our puzzle, particles suspended in the water. Let's start with green water. That color in many lakes and coastal areas is almost always a sign of life. Specifically, microscopic organisms called phytoplankton. Like plants on land, phytoplankton are filled with green chlorophyll, which they use for photosynthesis. Chlorophyll is fantastic at absorbing light for energy, but it's picky. It primarily absorbs red and blue light. What doesn't it absorb? Green light. It reflects green light away.
So, when you have a lot of phytoplankton, the rules change.
Sunlight enters the water, and the water itself absorbs the reds. But now, millions of tiny chlorophyll engines are also at work, absorbing a great deal of the blue light that the water would normally scatter.
With both red and blue light being removed,
the dominant color left to be reflected back to our eyes is green.
the more phytoplankton, the greener the water.
But what about that otherworldly, opaque turquoise you see in places like Lake Louise in the Canadian Rockies? That's not life, that's rock. These lakes are fed by melting glaciers.
As a glacier grinds down a mountain,
As it pulverizes the bedrock into a superfine powder called rock flour. These tiny mineral particles are so light they stay suspended in the water, making it look milky.
These suspended particles are fantastic at scattering sunlight. As sunlight enters the lake, the water absorbs the red and orange wavelengths. The remaining blue and green light then smacks into these rock flower particles and is scattered back toward the surface with incredible intensity. This intense scattering by particles, rather than just water molecules, is what makes the water look so bright and opaque. The minerals are particularly good at scattering the remaining blue and green light, which mix to create that signature, vibrant, milky turquoise hue.
Finally, there are the browns and yellows.
This color is usually from sediment and dissolved organic matter. When a river floods, it carries tons of mud and silt into the ocean, which mixes everything back together and results in a murky brown or gray appearance. Another source of brown comes from tannins. In areas with dense forests, decaying leaves and roots release tannins into the water. Compounds similar to those that give tea its color. They act as a natural dye, staining the water a transparent yellow or brown.
So, the final color of any body of water is a complex cocktail.
It starts with water's intrinsic blue. Depth and the seabed can shift it between navy and turquoise.
And finally, any particles within the water, be it life, rock, or dirt,
Add their own twist to the palette.
Every time you look at water, you're seeing a story told in the language of light.
From the physics of a single water molecule
to the geology of a mountain range, the colors of our planet's water are a beautiful reflection of the world around and beneath them. What did you find most surprising? The fact that water has its own color, or the way tiny particles of rock can change it so dramatically? Let us know down in the comments. And if you enjoyed this, make sure to subscribe and hit that notification bell so you don't miss our next exploration. In the end, water's color comes down to a beautiful interplay of 4 key things. First, the intrinsic color of water itself. Its molecules are great at absorbing red light, which lets blue light pass through, giving all water a faint blue tint. Second, depth.
In deep water with no bottom to reflect light, this effect is magnified.
The water becomes a colossal filter, swallowing all colors except for the blue. That it scatters back to our eyes, resulting in a deep navy. Third, the seabed. In shallow, clear water, a bright sandy bottom acts like a mirror.
It reflects sunlight back up through the water,
allowing the water's natural blue to mix with surviving green light, creating brilliant turquoise hues. And fourth, particles. From the phytoplankton that make water green. To the glacial rock flower that creates a milky turquoise. To the river sediment that muddies the coast. Anything suspended in the water adds a final, dramatic twist to the color. So when you're looking at a swimming pool, an alpine lake, or the vast Pacific, you're not just seeing water.
You're seeing physics, chemistry, and geology all working in concert.
You're seeing a story of what was absorbed.
and what was scattered.
And that is the simple, beautiful science behind nature's most stunning colors.